Welcome to Unit 4. This unit's going to be all about applications of derivatives, and there are basically 4 different kinds of applications that we'll talk about. The first is position graphs. You're actually looking at an example of a position graph, and it's a graph where you can relate the location of an object to its velocity and acceleration. And there's a relationship between these 3 curves, which we'll talk about. After position graphs, we'll go on to talking about optimization, then something called linearization, which is a way to make predictions, and we'll end with related rates. Here's where we start today, lecture 4.4a. The objective is that by the end of this lecture, you understand the relationship between position, velocity, and acceleration, and you can use those relationships both when you're looking at graphs and when you're looking at word problems. That's what I'm expecting you to be able to do when you come into class tomorrow. Understand that fundamental relationship. If you remember, way back when we started derivatives in October, we talked about the meaning of a derivative, and we said when we're talking about applications, the meaning of a derivative is that it measures change. And to be really precise, it measures how one thing is changing with respect to something else. And it's important to be clear on what that something else is. So in these 3 scenarios, we could be measuring where the car is with respect to time, or how steep the slope is with respect to where the person is on the hill, or we could measure how quickly the population is growing of the fruit flies in the experiment. When we talked about each of these examples, the truth is we were actually simplifying things a little bit, because in any given situation, there's actually a lot of different things that could be changing that you might be interested in. Take the example of the race car. You could be interested in where is the car. That would be measuring the position. You could write a function for it. Or you could be interested in how fast it's traveling, which is also a function because it could be changing. At different times, the car is going different speeds. So those are 2 separate functions, but they're also related. And that's because speed is really a measure of change for position. If we say, how is the position changing? We're really asking, how fast is it going? So in some ways, velocity and position are 2 separate things, but they're also related. To be really specific, velocity is a measure of how a position is changing. And then we can talk about acceleration. Is the foot all the way down on the pedal? Is he speeding up or slowing down? Which might seem initially like a totally separate question. It's a function. He'd be speeding up at certain times and slowing down at other times. But it's actually also a measure of change. And acceleration is a measure of change in velocity. If the speed is changing, it means he's accelerating, either speeding up or slowing down. So once again, this is kind of another question we could ask, but it's also a related function related to velocity's change. Jerk is actually the term for how acceleration changes. It's not something that comes up a whole lot unless you're in a physics class, but if you've ever driven in a manual car, sometimes if the driver isn't a great driver, or if the car has a faulty clutch, you'll feel this jerking when they change. And what you're feeling actually isn't how fast the person's going, and it actually isn't whether or not the person is accelerating. It's whether or not the person's acceleration is changing. If they accelerate quickly for a second, but then they stop accelerating, you'll feel a jerk. So jerk is a measure of how acceleration is changing. We'll pause here just to see if this is making sense. If you think of these questions as functions, what's the independent variable? These are all the outputs. What independent variable would we use? Right, exactly. We would use time. So in all of these cases, you're measuring acceleration as a function of time, velocity as a function of time. And the second question is there to make sure you're paying attention to the fact that all 3 of these are rates. So when we initially said that the derivative is the instant rate of change, that's true, but the instant rate of change of what is an important question because we could be taking the derivative of different functions. So let's work on some more precise definitions. The position function is when you write a function or draw a graph that tells you where an object is. So maybe this graph tells me where that race car is. It starts out 0 miles away from home. At some point it's 120 miles away from home, and then it turns around and comes back down to 40 miles away from home. That's a position function. The input is time and the output is distance. If we ask the question, how is the car's position changing? We then end up with a new function, which is the velocity function. Velocity is the derivative of the position function, and you can think of it as its own graph and its own function, but it's a related function. This function, which is different, it has a different output, is related to the distance function, and you can see some key points that you should recognize. For example, when the distance function has a maximum, it means that the car isn't getting farther away or closer. It's not moving just for an instant. That's because the velocity is 0. You can see that when the distance is increasing, the values, the y values of how fast the car is going are positive. That makes sense. They're traveling away from where they started. Similarly, when the distance is decreasing, they must be traveling back towards where they started, which means they're traveling in the negative direction. Acceleration, this will be a new one, is actually the second derivative of the position function, which also makes it the derivative of the velocity function. If we say, is this person speeding up or slowing down, we're asking, how is the velocity changing? Well, notice here in the beginning, the velocity seems to be increasing, and that's why acceleration has a positive value. Over here, this whole section right here, velocity is decreasing, which means the person's slowing down, which is why acceleration is in the negative area. At this point in the course, you should be pretty comfortable reading an original graph and answering questions about rate of change, but it's time to also start getting used to reading the derivative graph. For example, looking at this velocity graph, there's a couple questions I could ask about it. So to explain those questions that you just answered, when we ask how fast is this car going at 5, if you're looking at the velocity graph, how fast is velocity? So you're just going to read the output. At time 5, the velocity is approximately 15 meters per second. If I say, when is this car moving fastest, and you were looking at the original graph, then we would have looked for where the slope was really steep. But if we're looking at the velocity graph, when is it moving fastest is when does the velocity graph have its highest values, and that's, again, basically around time 5. If I ask, when is this car start to slow down? Well, slowing down is when you see the velocity decrease, and you can see it's decreasing here. So I would say maybe at time 7 or 6, it starts to slow down. Another question you could ask is, what happens at time 15? Yeah, exactly. So if the velocity is switching from positive numbers to negative numbers, it means this person's just turned around. So at time 15, the direction that they were traveling in switched. We'll get some more practice with that in class. Once you understand the 3 basic functions we have, we can start to apply them to situations that are separate from graphs. For example, we could talk about tides. So if any of you have driven past Route 80, where it joins 580, and you can look out at the water, you'll notice that sometimes the water's really high, sometimes it's really low, and that's because of the tides. Well, you can model the tides using simple functions, and in this example, they're going to ask you to interpret an equation that tells you how high the water is. The problem says the height of the tides in Venice are modeled by this equation where t is measured in hours. And then you're asked to write equations for the velocity of the water and the acceleration of the water. See if you can do that. Right, so we're given a function whose output is the height. And we're asked to find equations for velocity and acceleration. For this problem, all you really needed to do is remember that when you have a function that tells you where something is, for example, how high it is, and the input is time, then velocity is the first derivative, and acceleration is the second derivative. So finding the velocity and acceleration just means taking the first and second derivative. And notice that there's a chain rule here. I did it all in one step, but I did multiply pi over 6 times the 14, and that's where 7 over 3 pi came from. Pause here if you need to check either the first or the second derivative. Notice how I showed my work. I gave a name to the velocity function, and then I said it's going to equal the derivative of h, and then I gave the actual equation on the next step. So this is kind of explaining where I got my answer. When you do your problem set, I'm going to ask you to show your work in a similar manner. So that seems pretty easy. Unfortunately, the truth is we don't walk around asking what's the velocity of that thing, what's the acceleration of that thing. In reality, we ask questions like, by how much is the tide's height going to change? I need to know. I want to go swimming. How deep is the water going to be? Or what time of day is most dangerous for swimming? And those are both calculus questions, but what you have to learn in this unit is to interpret what exactly is the calculus inside that question. And once you see what the calculus is, actually doing the calculation is really easy. You already know how to do all the derivatives. So here are some tips. When you are reading a word problem and trying to figure out how to set it up, you want to orient yourself to certain keywords. Words like where, how far, height, distance, or displacement are words that are keying you into the fact that you're probably going to be working with the original function, the position function. Words like how fast, or when does it stop moving, or at what time is it moving backwards, are asking you about the velocity. Speed could also be asking about velocity. Be a little careful with speed because velocity can be positive or negative, basically because you can be traveling in a positive direction or backwards in a negative direction, but speed is always a positive number, so speed's actually the absolute value of velocity, but that would be related. Finally, words like speeding up and slowing down, or the rate of change of velocity, those are asking you about acceleration. We will rarely encounter questions about jerk, but you should know that it exists and recognize the word. Do be warned that you need to be careful when you see the words time, rate, and average. And that's because these three words actually aren't particular to any one of these three functions. And so you're going to have to continue reading to figure out whether they're asking you about time in relationship to velocity or acceleration or position. Similarly, both velocity and acceleration are rates. Velocity is the rate of change of position. Acceleration is the rate of change in velocity. So just because you see rate doesn't mean you're going to have a first derivative. And that's the big, big, big warning. Time, as you know, is the independent variable. So it often means that you're going to be solving an equation. This is something that you should make note of in your notes because it's going to come up in tomorrow's problem set. If the question says something like, at what time is the distance 5 meters? You're going to set up an equation using a position graph, but you're going to solve for time. Similarly, there could be a question that says, at what time does the vehicle stop moving? That means you're going to set up an equation using the derivative, but solve for the variable time or x. Finally, average is different than instantaneous rate. Instantaneous rate is either a velocity or an acceleration, and you plug in a number. When you calculate averages, you're going to use the slope formula, and I'll do an example in just a minute, but just remember that average rate of change is not actually a derivative. Before moving on to some practice problems, I just want to check your understanding of these concepts. Look at question number 1 below. What calculus strategy would you use to answer this kind of question? Exactly. So hopefully you recognized how fast is a keyword for velocity and that we're given information about time. So most likely to answer this question, we would be calculating a first derivative and plugging in 3. How about number 2? Yeah, exactly. So how far is a keyword for distance, which means it's the original function and we're still plugging in because we're given time. How about number 3? This is where it gets tricky. When did the car stop is asking you for time, which is not enough information to figure out which function we're going to use, so you have to keep reading. It says, when did the car stop? Stop means not move. In other words, we're talking about motion. So actually, we're going to be using the velocity function, which is the first derivative, and we're going to set an equation. We're actually going to set it equal to 0 because we want the velocity to be 0. That's what it means to be stopped. And then we're solving for t. Try number 4. Great. Speeding up or slowing down is acceleration. Again, they give you time. So you're going to find the acceleration, which is the second derivative, and plug in 6, and then you're going to look at whether it's positive or negative. How about number 5? Excellent. 5 is another equation that you set up, and it's a velocity equation.